So today what we want to do is to look at the elastostatics in higher dimensions. So we're gonna go through this roughly quick because it's going to be the same thing we did last time, right? So if you see on your right, we have the same problem. So these are mechanics potato. We call our domain omega, right? The boundary we define it as the closure minus the open set. As usual, this is the same stuff we have done over and over, and we define the boundary as mutually exclusive sets. One part of the boundary where you're applying the essential boundary conditions, the other Newman, and the other one the Robin. Okay. This is the same as before, and what we want for the elastostatics problem is to define certain quantities. So we have sigma, which is our stress tensor, and if you remember, this is the way you define a tensor. So this is the domain is omega bar, and then the codomain is a tensor RD cross RD. And the same thing applies for the others as before, only that now that we're basically dealing with an elastostatics problem, then we have the displacement field. And that displacement field has how many components? So 3 or 2 if you are in 2D. The problem that you're going to do in the project is a two-dimensional problem, so you're going to have 2 degrees of freedom per finite element node. Okay. So we define the body force, and then prescribe displacement, prescribe tractions, and we also need to define, if you remember, this elastic support H. We call it H because of the analogy with heat convection. But once we have all those definitions, so I copied this to gain some time. Basically, we go back to the strong form of the problem. And in this case, the strong form is given by, let me just put this up, otherwise I'm not going to have space. The divergence of the stress tensor plus the body force is equal to 0. Now it's 0 vector, so we have 3 equations if we're in 3D. And this has to be true at any point in that domain omega. And of course, then we're left with the boundary condition. So as before, we have to enforce U is equal to U bar on omega U, gamma U, which is a part of the boundary where we are enforcing the Dirichlet boundary condition. We have the Cauchys expression. So the stress tensor dotted with the normal to the boundary. So if you see here, this is the definition of the normal to the boundary, is equal to my applied tractions that I call T bar, and this has to be valid on gamma T. And then I have one more, which is the same thing. So the traction has to be equal to some tensor dotted with the difference between the prescribed displacement and the displacement at the boundary. So this is gamma U on gamma H. And that's it. This is basically the strong form of the problem. As we did before, in order to satisfy that, to satisfy that equation point-wise is very hard. So what do? We come up with a weak formulation of the problem, or variational form. And for that, we need to define some spaces, right? And we will talk about the spaces. But just to complete this, by this is basically, I mean the divergence operator is the same thing, right? You're going to find that written in both ways when you read papers or books, right? This is the divergence operator. We are going to assume some constitutive law, so we assume that our stress tensor behaves linear. So this is Hooke's law. All of you should be familiar with this. Yeah. And then we are going to also assume that we're dealing with a small deformation, or we're not doing finite strain here, so everything is a small deformation. And therefore, our strain tensor can be defined as 1/2 of grad U plus grad U transpose only. So I'm not taking the other grad U transpose grad U term that would be required to really express the kinematics properly in large deformation. So this is going to be the linearized strain tensor. Okay? Okay, so how do we come up with our weak form? Who can remember? Yeah.
Use divergence theorem and that thought to go from divergence of sigma to sigma times.
Yes, we will get there. That is what is coming in the weak form. Okay, it's basically the same thing we did last time. So who can remember what do we do to come up with our weak formulation or method of weighted residuals? Huh? See, it is the same thing you all should remember. So who can tell me? What do we do? We multiply by W, but now our equation is a vector equation. So W has to be what? A vector. It's a vector valued. And then we have the divergence of sigma plus B. We're integrating all of that, and we're saying that this is equal to 0. 0 scalar or 0 vector? Huh? Scalar. Very good. Why? Dot product should give me a scalar. Okay? So this has to be valid for all vector valued functions, right? That belong to some space, and we have done this already. We know where to take those functions from. So in a vector valued problem like elastostatics in 3D, what we need is a vector, right? That means that vector has, let's say in 3D, 3 components. All we need to satisfy is that those 3 components belong to the same space that we defined before, right? So if we're working with these Sobolev spaces that we discussed are space of functions that are square integrable up to the whatever order you are, requiring that Sobolev space, then now each component of that vector has to be in that space. That is the only difference when we're moving from 1D to higher dimensions. Okay. So let's define that space as a set of functions V, yeah, such that V of X is basically a vector. That means a vector RD. So we are in D-dimensional Euclidean space for all X in omega, and then what we only need to do is to satisfy that every component Vi belongs to my H1 of omega space. And there was another one requirement, if you remember, of that V space. What was the requirement? If you remember, what was the trick that we did to get rid of the reaction? Huh? Yeah. Of course, we are assuming that this is also it's part of the energy space, right? Keep in mind that the moment we are working and we're saying this, we're already working with the square integrable functions. Okay, so it is impossible to take functions from that space whose finite strain energy goes to infinity. Okay, all of the functions that you take from that Sobolev space are square integrable. But there was one more requirement. Remember, we had a trick to get rid of the reaction force. What did we say? Yes, that is the answer. So what we're saying is that V, or the restriction of V on gamma U, which is a part of the boundary where we are applying the essential boundary condition, that should be equal to 0. So that looks quite mathematical and a bit complicated, but it's very simple once you know how to read this sort of thing. So this says, well, V naught is the space or the set. Those braces are denoting a set of functions, vector valued functions, because now I'm working with vectors. So vector valued functions V such that V evaluated at any X, right, is a vector. And that is for every X in that domain I'm interested in, such that Vi, right, every component, I could have put after that I goes from 1 to D. right? To make sure that I'm talking about every component, but well, let's leave that aside because it's understood, it's implied, such that the restriction of that function or that function being evaluated at the part of the boundary where you're applying directly boundary condition is equal to 0. That's all it says. So now that we have those functions, then what did we do? Who can tell me?
Excuse me, I didn't understand. Vi, a member of H.
H1. Yeah. So if you're taking a function v, right? Say this is a vector value function, so it's going to have v1, v2, and v3. These are functions. So what we're saying is that every one of these components has to be taken from that space. Yeah? That's all it says. Okay, so what do we do? If you remember last time we used an identity. Now we're going to do the same, but this time we're going to demonstrate the identity properly so that we all see where that is coming from, because there are a couple of tricks. But we use this identity as a means to do the equivalent of integration by parts in 1D. Okay? So what we say is that if we take this term here, yeah, I say that, well, this guy dotted with, let me just like this. So I'm saying that that is the divergence of the stress, and that divergence of the stress, since the stress is a tensor, the divergence of the stress is what? A vector. Yeah. So that divergence of the stress dotted with W, and then we're going to say is equal to the divergence of dotted, let me see, sigma transpose like this. So now this time we're going to prove this. So what we're having here on the right is basically the divergence of the transpose of a tensor that is being applied to a vector. So a tensor applied to a vector, what is it? A vector, right? So now we're taking the divergence of that. Yeah? So this is what we're going to do. So if you take that component, let's see what this guy is here. So sigma transpose dotted with W, what is this? Well, you can say that sigma transpose is sigma ij, ej, tensor ei, right? So you see I flipped. That's going to give me the, let's say that gives me the transpose of a tensor. I could have done the same by saying just sigma ji, and then I reverse the other two vectors, but it's the same. And then I have to do the dot product with that vector W, and that's basically wk ek, right? So that expression, if I basically put everything that is constant to the left, I'm going to do sigma ij wk, and by definition of how you apply a tensor to a vector, this is basically ei dot product ek and then ej, and all of you know that this guy here is the Kronecker delta ik, and the effect that has is basically contracting one index, so all that expression is equal to I sigma ij wi ej. Of course, this is vector. And then you see that all that expression is basically a tensor applied on a vector, the result is a vector, and you can say that whatever we have in front, this guy, right, is basically the jth component of that vector. Yeah? So far so good, but now we have to take the divergence of that thing. And what is the divergence of that thing? Well, we know that the divergence of a vector, let's take some arbitrary vector v, by definition is, so what is it? Is a what? The divergence of a vector is a scalar. So is the derivative of v, since we're working with j components, let's make it simple. Let's say the derivative of vj with respect to xj. Yeah, so if I apply the divergence on sigma transpose dotted with w, is basically I have to take the jth component of that vector, which is sigma ij wi, and take the derivative with respect to xj. Right? And now, since we have the derivative of a product, that's going to be equal to the derivative of sigma ij with respect to xj wi plus sigma ij, the derivative of wi with respect to xj. Yeah? So you can immediately recognize that this one here, right, that is just the divergence of the stress tensor, right? Because as the divergence of a tensor can be written as the derivative of the ajth component of that tensor with respect to xj ei. So that is the divergence. So if you look at the sigma ij and then I have tij, is the same thing, right? And that is being dotted with our vector w. And then for the second part, this is an interesting operation that probably you have not come across with in your previous classes. But if you have an operation between tensors that looks like this is basically defined as going through each one of those components of the tensor and doing some sort of dot product between those components and then adding those together. Yeah. And so this guy here is the stress tensor with the gradient of that vector, which is also a tensor. Yeah. Yeah, contraction. So if you remember the gradient also of a vector, and I'm gonna take a vector w, is just defined as the derivative of bi with respect to xj and then ei tensor ej. And so now we have proved our identity. This time I wanted to do it so that so that for the case of heat conduction, then which is much simpler than this, you understand how this is done if you just didn't know up to now. Okay, but now that we have that expression, so we go back to our identity. Yeah. Now we're gonna plug that back into our weak formulation. Yeah. On the right, sorry. This one. This is the gradient of a vector. It's a gradient. So you need to let's say upgrade to a tensor so you can do the contraction between that tensor and the stress. No. That's a Remember that when I put one bar under, that is basically either a vector or a tensor, right? This is the way I use notation. So some of you use two bars, but in the end, when you go read a paper, it's either bold or not bold, right? It's just the way it is. Okay. So now that we have that, what we're going to do is to plug that identity back into our equation, and then we get a much better expression for our weak form. Sigma I'm not considering yet the body force, right? Because I want to analyze this expression in detail. So I just took, if you look back at our equation, right, I am just taking this part of the equation and I'm plugging back the identity, and what I get back is this whole thing. So now what I would like to do is basically to work with this part instead. So I'm replacing the left-hand side by the two terms on the right-hand side. And what you can immediately see, right, is that there is one integral where we have our friend the divergence, right, being applied to that vector, which is sigma transpose applied on W. But that gives us, if you remember, we look at this divergence theorem where you can actually transform that integral over the entire domain into an integral over the boundary. So what we know is that if we apply the divergence, or let's write it better, the divergence theorem on that, I'm going to have basically an integral over gamma of whatever is inside that divergence, which is in this case a vector, dotted with the normal to that boundary. Yeah? And by the definition of the transpose of a tensor, I can actually replace that whole expression by sigma dotted with n, and that is great. Who can tell me why? And this is basically the definition. How do I get there? Is basically u dotted with t operated on v is equal to v operated with t transpose u, just by definition of a transpose. And who can tell me why this is great? What do we have here? Huh? We have attraction there. So that is great because I can transform that integral. I can take that integral and basically, since we have three boundaries, how many integrals do we have? I mean, we have divided our boundary of our entire domain into gamma u, gamma t, and gamma h. So how many integrals I can replace that for? Huh? 3. So one is going to be gamma u, where I'm going to have my w dotted with my reaction force. I'm going to have another term that is on gamma t, which is the same thing but dotted with my prescribed tractions. And I'm going to have the last one on gamma h, which is my Robin boundary condition, with this guy dotted with my h. You remember that tensor, and then u minus u here like this, d gamma. So I have three terms. What do I do now? Who can tell me? What do I do now? Can I simplify that expression? Not yet. Can I get rid of any of those integrals? Huh? Yes, you are right. This term is 0 because of what? Yeah, so because we have taken our weight, our vector valued weight functions, right? So that the restriction of those functions on omega u is equal to 0, right? Then I can get rid of that term. Now, if we put all these things back, now there is one more thing that I want to mention here, that because sigma, we have not assumed any form of sigma, but it turns out, as you all know, that sigma is actually a symmetric tensor. right? And this is because of balance of angular momentum. It turns out that you can write this expression as just taking the symmetric and of course that is defined, this guy here, the symmetry of W is defined as 1/2 of and this is basically, if you look at it, our linearized strain. In a way, it looks like a linearized strain. Now, when we are going to write the full equation of the weak form, then we are going to make a comparison with what people usually use in you know, when they present the same formulation through the principle of virtual work. Okay, that's what we're going to do now. So then our weak form is find U belonging to that space such that, again, our bilinear form is equal to the linear form. This remains the same, and this is for all V in that space. Yeah? Now, if we're looking back at all the elements or those terms that contain both U and V, what do we have? Let's see. We see that we have one here, right? Because this term contains both W and U, right? We definitely see that we have this one here, because even though you don't see U explicitly, well, it's implicitly defined in the way the stress tensor is defined, right? So you have your constitutive tensor multiplied by strain, and strain is a function of U, so that term is also a function of U. So then our bilinear form is going to be composed by plus gamma H, and then we have this guy. And then the linear form is basically everything else. So we're going to have, remember that we have our body force, right? And then the part of the boundary with gamma T. I missed one here. And then finally, the other component of the Robin boundary condition applies here, which is the known component. And that is our weak equation. And this is basically what we solve. Yeah?
What is this symmetry?
Yeah, so when your stress tensor is symmetric, right, you can show that it's the same thing as applying this operation on the stress tensor. It's exactly the same thing. So you basically, this nabla S is a means for me to simplify this notation. It's the same thing. You can show it's the same thing.
But you apply that on the stress tensor. You apply it on the...
Yeah, still, the operation holds. This whole operation is what I'm interested in, this whole thing. And because of the properties that the stress tensor is symmetric, right, this operation holds. So I can take W, the symmetric part of W, and then do the contraction with the sigma, and because sigma is symmetric, this same operation holds. I do this because I am really interested in expressing that W as the linearized strain. Because if you look back at my this expression that I got from the bilinear form equals linear form, what you see here is that if I take a look at that first term, the symmetric part of W is like a virtual strain, right? And for example, this term here would be the virtual work done by the applied tractions. right? So you can put again, coming from the method of weighted residual, which is what I like to do, or coming from the principle of virtual work, is exactly the same thing. So now that we have this, well, you know, yeah. Sorry. Yes. Thank you. Yes. Thank you. I think I erased to put the gamma, the omega. Okay. So what happens if you have non-homogeneous Dirichlet boundary conditions? Who can tell me? Who remembers? Because it's the same thing. Huh? No one? Come on, guys. We have done this 3 times already. Who remembers? We define. Yeah. And this is called, we define. Oh my. Okay. We define. How was this called? Linear variety, and we said that it's basically a translation of a space by some known vector. So I'm taking every function in that V0 and I'm translating that function with a vector that I know is going to comply with the applied boundary conditions, right? So the restriction of gamma u is basically equal to my prescribed expression. Okay, that's all we do, and everything else stays the same. We replace our bilinear form by so we take basically a function from that space. So let's do that. So given u that is going to be equal to v plus that u tilde, yeah, find the unknown component of that, the unknown component, because the u tilde that we know, such that the bilinear form is equal to the linear form. And if you remember, what happened when we did this trick is that whatever you know about the essential boundary condition was going to show up in the right hand side, and modify eventually your force vector. And this is a very nice approach, because what you see is that again u and v are taken from the same set of functions v0. You had a question? Sorry? 3 lines above. Why do I? I'm a bit close. Where you are looking at? Can you show me?
The lines that you see right now, above 3 lines, why do you not do W instead of V?
Oh, because W here is a weight function.
Yeah, okay.
Here is a weight function. But what I'm doing here is I'm basically defining what it's called a linear variety. I'm still not talking about W here. Huh? I'm just saying that the functions I'm going to use, right, are going to be a combination of a function that is taken from this V0 plus some function that I know is going to satisfy the essential boundary condition. I'm not talking about W yet. Now, once you take that function and you say, well, I'm going to take, for example, here's the way that function is written, right? That function u taken from that linear variety is going to be equal to v plus the u tilde. U tilde we know that is going to satisfy the boundary condition, right? Now v in that case is the unknown part of that function. Yeah, this is a function that our trial solution that we're going to plug into our bilinear form. So when you do that, you see that this is not known now. That's why it shows up at the left as the bilinear form of v and w, and whatever you know, which is this guy, shows up at your right hand side. So it's modifying your force vector again. So that is the little trick that we did, right, to get around the fact that sometimes we need to enforce non-zero Dirichlet boundary conditions. So this is basically is it clear? Huh? It's clear. Okay. All right. So, well, once we have that, we have basically everything we need to know. This is, again, the infinite dimensional equation. So to get into something that we can solve, what do? Huh? We discretize. By that, we use Galerkin. We're taking the trial solution and the weight function from the same space. Now it's finite dimensional space. So all we have to do is take that equation and replace u by uh, v by vh, w by wh, and then that is now our finite dimensional form. That then we discretize and we get our system of linear equations ku equals f, and that's it. It's exactly the same thing as before. So the only things that changed in all of this three-dimensional mess, well, we had to prove this expression, right? But other than that, we apply the divergence theorem here. This is the same as we did in heat conduction. And then we got rid of that term that contains a reaction because of the way we're choosing our weight functions. And then we are left with an equation that we can actually discretize and solve. So there are a couple of other things, of course, but in the interest of time, because I really want to move to something else, let's take a quick break here. The rest of the things that I would like to discuss on this are all in the notes. So please go and read the notes. Everything is very well explained. I think we can make a better use of the time in class for doing something else now, okay? So now let's take a quick break and we'll see you in 5 minutes, right? 5 minutes.